Bom dia, pessoal. Peço perdão pelos problemas técnicos que nós tivemos. Então, vamos começar com o Naufal Hatim. Good morning, everybody. We are going to present Naufal Hatim. He's a PhD candidate in the Laboratory of Applied Mathematics and Scientific Computing at Sultan Moulay Silmane University in Morocco. He works with stability of solution for psi-Kaput fractional differential equations, with time delay, and with numerical analysis of fractional forms of Newton's Coulomb law. Thank you so much, Naufal. Sorry if I'm not pronounced correctly. And we're going to start the video.
Good morning and good afternoon, everyone. It's a pleasure to be here today at the third Brazilian Symposium on Fractional Calculus. I want to extend my sincere gratitude to the organizer for this opportunity. My name is Naufal Hatim from the Laboratory of Applied Mathematics and Scientific Computing at the Sultan Moulay Slimane University in Beni Mellal, Morocco. So this is a joint work with my supervisors, Professor Mohamed Al-Omari, Professor Ahmed Fadl, and Professor Saïd Al-Miliani. I am excited to present our research titled A Fractional Newtonian Approach to Modeling Blood Drug Dynamics. Thank you all for taking the time to attend our presentation. We hope you find our work insightful. So let's get started. So this is the outline of the presentation. So we'll start by introducing the classical Newtonian model of Coulomb, which serves as a foundation for our work. Then we will delve into the preliminary, defining the key concepts, such as the psi-capital fractional derivative. Then we will discuss the existence and uniqueness of solution to our fractional model, proving that under certain conditions, a unique solution exists. Next, we'll investigate the concept of finite time stability for our model. And finally, we'll apply our model to a pharmacokinetic study of drug distribution in the body, comparing our result with the previous one. So let's start by revisiting a classical concept in physics, Newton's law of Coulomb. So imagine a hot cup of coffee cooling down in a room. So Newton's law of Coulomb describes how the temperature of the coffee changes over time. It states that the rate of which the coffee cools is proportional to the difference between its temperature and the temperature of the surrounding air. So this is represented by a simple differential equation. So if we consider U of S as the real-time temperature, then the equation F1 captures the exponential decay of the temperature difference. Solving this equation gives us a clear mathematical expression of how our coffee cools down, approaching the room temperature over time. So recently, Almeida modified the classical model F1 using the psi-capital fractional derivative instead of the classical one. So we get the model F2. The solution involves the Metcalfe function, a generalization of the exponential function. So building on Almeida works, we proposed the model F3, a model with time delay. So a full study of this model was done. So based on the three models, this inspires us to look at a more generalized problem. The problem one. So here the function f represent the ambient temperature, a variable ambient temperature. In the previous model, the temperature was a constant. Here E and B are two heat transfer coefficients. So now, before analyzing our model, let's review some key mathematical concepts. So the Almeida kernel space over the interval EB, defined as the space of functions psi that are in time continuously differentiable. Moreover, the first derivative of psi must be positive over this interval. So using this notation, we recall the definition of the left Riemann-Liouville fractional integral of u of order alpha. The fractional integral of u in this case is defined as the following expression. So recently Almeida introduced a fractional derivative with respect to another function as the following. So under the condition of the last definition, we can rewrite the left psi capital fractional derivative using the following expression. So the main question here is why we should use the psi capital fractional derivative. So there is two sides. First one is theoretical. So for a suitable choice of psi function kernel, the psi capital derivative reduced to some well-known fractional derivatives such as capital and capital Hadamard and other fractional derivative. From a modeling point of view, it gives a more flexibility to model some real-world phenomena. So here we give a proposition, two crucial properties of the left psi capital derivative. So first one, the derivative of the fractional integral gives back the original function, and the fractional integral of the derivative almost recovers the function. The difference is a polynomial depend on the initial value. In case of alpha belong to 0, 1, so the polynomial reduced to the initial data u0. So let's turn to our main problem. So now we give important result. We transform our problem to an integral problem. So a solution to our main problem if and only if u satisfies a delayed Volterra integral equation. This is a direct result from the previous proposition. Here we go to prove the existence and uniqueness for our problem. So if the sum of the absolute value of E and B is less than this expression, then our problem admits a unique solution. This is a direct result from the previous proposition. We defined an operator on a specific Banach space. This condition, based on the previous proposition, this condition here ensures that our integral operator is a contraction mapping. So via Banach space fixed point theorem, we get our result. Now we go to the finite time stability. So model 1 is finite time stable with respect to those parameters if and only if the initial condition is bounded. The initial condition is bounded implies that the solution u of 1 is also bounded by a specific constant beta which is greater than delta. Now we give an intermediate result. So the problem is finite time stable with respect to those parameters if the following function is less than beta. So for the idea of the proof, we use here a Henry-Gronwall tape inequality with delay. We apply this to the first proposition, the proposition which give the equivalence between our main problem and the delayed Volterra integral problem. So using this proposition, we derive a more simple criterion. So under the condition of theorem 4, for all positive epsilon, the model is finite time stable with respect to those parameters where the beta epsilon defined as the following. Now let's turn to the application of our model in pharmacology. So the first question here is, what is pharmacology? Pharmacology is the study of how medicine works and how they affect our body, while the pharmacokinetics study how drugs move through the body over time. While studying pharmacokinetics, both experimental and theoretical method must be taken into account, mainly mathematical models. So, in order to model the 4-boson drug distribution in the human body, that means the entirety of the dose is absorbed directly into the bloodstream via injection, for example, we use the most simple way by considering the body perform its function as a unified whole. That means we treat the body as a single well-mixed compartment. So this is what Ahmed did. He introduced the following model. So the drug concentration follows an exponential delay. So this model is described by simple first order differential equation, what we will name the classical model 2. So here the parameter E is a negative constant. The solution is an exponential function. So Audal modified the classical model 2, but they replaced the ordinary derivative by a left psi-capital fractional derivative. So the new model, the model 2 becomes 3. This is what we will call the fractional model. So the solution involves the Metagloff function instead of the exponential. So let's look at some experimental data to test these models. This data came from a clinical study of an antibiotic level in a patient. So blood sample were taken over 6 hours after the drug administration. The table shows the drug concentration at various time points. So we'll use this data to compare our model with the existence approach. So for that, to compare this model, first we step into the numerical investigation. So we use the model 1 with an ambient temperature equal to 0. Secondly, we conduct the simulation over the interval 0.6 with n equal to 600. It's the number of the subdivision, and also with a time delay equal to 4.8 minutes and the following initial condition. We use the same optimal parameter for each of the classical model and the fractional model 3. So we get the following result. Before we give the result, we will use the Euclidean norm to measure the absolute error between the model prediction and the experimental data, and we'll use the relative error that will be calculated as the ratio of the absolute error to the data norm. So this metric will help us to quantify the accuracy of each model. So this table summarizes the result of the result of the models comparison. We see that the fractional model outperforms the classical model in terms of absolute and relative error, while the model 1 provides the most accurate prediction. So to gain further insight into the model comparison, we can calculate the percent error, which is simply the relative error multiplied by 100. So this helps us to visualize the relative accuracy of different models. So in a more intuitive way, we see that the fractional model with delay 1 exhibits the lowest percent error, highlighting its superior performance in capturing the experimental data. So, as in 4, the article, an article of Almeida, we introduced the gain of the efficiency. So to quantify the gain of efficiency of a model compared to a referential model, we introduce this metric in the same way. This metric is calculated as the difference between the percent error of two models divided by the percent error of the reference model and multiplied by 100. So the reference model is chosen as one with the highest percent error among all of the models. This metric provides a clear comparison of the model relative performance. So as we see, model 1 has a great efficiency gain with respect to previous model 2 and 3. So this result shows the accuracy of our proposed model, which prove that fractional derivative give a more realistic view of some real world phenomena, and also to get a clear insight of this experimental data, we give this plot of the experimental data versus the tree model under the same parameter used in the previous type. Here, as we can see, the data is represented by the blue stars. The classical model is the blue one. The fractional model is represented by the green plot, and our model 1 is represented by the red one. So as we see in the plot, the solution of the classical model 2 is quite far from real data, whereas the solution of the fractional model is somehow close to some data and far from other data simultaneously. But the solution of our model match all the data and pass through all of them. So the graphical representation demonstrates that the proposed model 1 is more realistic than its predecessor. So the drug concentration value in plasma predicted by our fractional model with delay closely matched to those observed in the clinical trial. So this clearly indicates that the model 1 provides the best fit to that. So thank you for your attention. We would be happy to take any question you might have. Please feel free to reach out to us after the presentation if you have any further inquiries, and thank you.
Thank you so much for your presentation. And we have some questions. First one, how regularity are the holes you working?
I think Professor Van Terler, sorry if I I pronounced the noun I didn't pronounce the noun correctly. I think he added another question. I think he clarified the question. We talk about why we choosing the in the definition of capital fractional derivative C1 instead of Sobolev space. Yes, is
Okay. Sorry.
it is
The
the same
first.
question.
Oh, yeah. We have the first question for José Vanteler. How regularity are the holes you work in?
I didn't understand the question. I think he 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 give more details in the third question, as I think. Yes.
Okay. We are going to ask him about more details. So we have another question from Professor Rubens.
Uh, Thank you so much,
Congratulations
Professor
for your
Robbins.
presentation. Yeah.
Uh, I in the first part of the presentation, I clarified this. There is two sides. There is the theoretical side and from a modeling point of view. From the theoretical side, for suitable choice of psi, we can get a large class of fractional derivative. But from this is the real motivation is a paper by Almeida. What is the best fractional derivative to fit the data? In that paper, Almeida use not only the suitable choice of psi, but another form of psi for several examples. He proved that this derivative is really from a modern point of view it's good, and for this we choose this derivative to build on this derivative.
Okay. And curiosity.
And about
How do you?
and
Yeah.
about how I hear about this event, it's from Instagram. Just by scrolling, and
Oh,
I
nice.
found a post about it. So this
Okay.
is the
Another.
yeah.
Okay. Another question.
Yes, about this question. So the work, it's like a movie. We start with the end. In this work, the main thing is that the model should be realistic. So all the theoretical things is at the end. So we we, we find that the model is is realistic more than the previous one. Then we go into the theoretical existence, uniqueness, and stuff. This, and we use the the definition given by Almeida, where he stated that the function should be in time continuously differentiable. So the regularity here is it's not really important. The the, main, the important thing is here is the model is realistic or not. The all theoretical things, it's at the end of the work. In the presentation, we start by existence, uniqueness, unit time stability, and the model. But in reality, the work starts from the end to the beginning.
Okay. Thank you. Another question.
Yes. For the advantage, I think it's the same question as the same question addressed by Professor Robbins. It's
Yeah.
giving more flexibility from a modeling point of view. Here, for the choice of psi, we choose psi equal to the identity because the previous fractional model used psi of s equal s. So to compare two models, so we choose the same psi. So if the previous model, for example, the choose for example psi equal to log s plus 1, we will choose the same psi to prove that our model is better. It's not depend on the specific side.
Okay, and
Right.
another congratulations.
Thank
And
you.
Nofel, thank you so much for your presentation. And
Thank you.
now we are going to the presentation of 11. And I'm sorry, we're a little late.
Have a good
And
day.
thank you. Okay, and thank you so much.
Thank you.